Okay, Kap. Welcome to the 5th class of Big Data Analytics. Let me start with reviewing the syllabus. Okay, I may have rearranged items a bit from the version you've got, but anyway. So anyway, we began with the first week on the discussion of the science of doing data, big data or otherwise. And again, I'm probably saying this for the 15th time. The key elements that make big data a phenomenon is the volume, the velocity, and the variety. In terms of volume and velocity, it's pretty much platform dependent, which means that if you are doing a fintech, maybe all the system is tied up in one big high performance computer, or maybe a big, fairly expensive, or maybe not so expensive anymore, a cloud subscription to the database. Or if you work for a really large organization, it would be a mixture of on-prem or on-premise as well as cloud. But either way, it's going to be a very big hardware and software integrated solution. And so that's going to involve some kind of distributed storage, distributed processing, and all that. We have all these Hadoop, Spark, all kind of system. So we are not going to really be able to explore that aspect of big data, that volume, that velocity. But we certainly are going to be dealing with the third aspect, which I suspect is the most important or most interesting thing to begin with. That is the variety of data. So we said that, yeah, the variety of data. So in this class, hopefully we'll have a lot of time to deal with different kind of projects, some with strictly numerical data, some with, say, categorical data, sometimes with audio, visual data, pictures, GIF file, whatever, okay? But since you guys have not really started with any kind of analysis class, except for the statistics, the good place to begin would be with numerical data. A more generalization of that is just categorical data. So you have some kind of description, some kind of labels. Okay, so it's not numerical, but still you can think of it as the sort of data that packs inside a big spreadsheet. Okay. So so even though, again, I promise that we will have opportunity to play perhaps with audio or visual data format, chances are for the bulk of the class, we are focusing our analysis, the analytics part, on data that comes in tabular or table form. Okay. So again, always think of your data, in this case, think of your data as coming in a big, gigantic spreadsheet. Okay. Now, of course, we're not going to work with spreadsheet. Again, it's very clumsy, right? With spreadsheet, basically, you have to highlight the table and whatnot, and you certainly have a lot of machine limitation in terms of number of column and number of row. And so when we work with spreadsheet, we have that kind of clumsy limitation to deal with. Fairly large data, not even big data. When we talk about big data, we talk about gigabyte, terabyte. But even something that is not that big can have too many columns and too many rows, and it would just be very clumsy, and sometimes not even doable. Sometimes the Excel wouldn't just open at all. So we deal with some kind of program. Now, when it comes to programming, we have two choices. One is Mathematica and one is Python. Now, for those of you guys who are going ahead and taking up the data intelligence, applied data intelligence track, you will need to learn Python. Not because it's that powerful, but it's because it's more ubiquitous. In other words, scientists, engineers, biologists, chemists, architects, artists, web page designer, these people if you have to ask them what's the common programming language that they can speak, chances are it is Python. Okay, so that's why the emphasis on Python for that track will become very important, because you can't get by without speaking Python to somebody. Okay? But for the rest of you, and even for the guys who are going for the applied digital intelligence track, Mathematica, first of all, it's a more powerful analytical platform. But for this class, the reason that I'm using it in this class is because a lot of things that you want to do, okay, a lot of the function that you want the program to perform for you is already embedded in Mathematica. So you don't have to go to a library and download the source code or download GitHub or anything like that. It's already built in. So you can, and it has a very powerful AI engine for interpreting what you want to do. Okay, so it's a very high level thing. It's very conceptual. It's very design oriented, visual oriented language. So if you're not going to be very keen on programming, and a lot of you are not really going to be that keen on the programming side, Mathematica is the right tool. Okay, it's the tool that you would be able to use to prototype your ideas, your application, your analysis, even when you go into health science, when you go into sustainability track, when you go to smart cities and whatnot. And of course, also for applied digital intelligence. In fact, like I told you, in my data science project, I usually lead off with Mathematica conceptual demonstration or analysis. Once I get to the model to the point where I'm pretty happy with the direction I'm going, then certainly I would ask my right-hand man, your TA here, to write up everything in Python, because that's the implementation language that is more ubiquitous with the industry. Okay, so that's why we have this second week. Okay, and then we have the third week, which is to introduce again to the concept of visualization. So data visualization, you have to remember, and I probably again have said this 15 times, visualization is going to be with you throughout. Sometimes you get the data, you visualize, and that's it. You get the insight right away just by visualizing it. Okay, and you get a lot of that in terms of like digital dashboard work, like identifying where you are losing money, where you're making money, which product is doing well with which segment. You don't have to do any kind of mathematical modeling or anything whatsoever. You just kind of visualize data, put variable X, juxtapose it with variable Y, and maybe X and Y and Z, and all kind of manipulation, maybe as a function of time, as a function of demographic, and so forth. So sometimes visualization already gives you insight. Okay, but of course you wouldn't have the rest of the semester, the rest of the term, learning this all machine learning, supervised, unsupervised learning, if you get insight right away, right? So you have to do some kind of analysis. Okay, now analysis, you have already done some analysis on data, and that is your statistics class. So in that case, you can think of statistical description as a numerical analog to visualization. Okay, you want to get a picture, right? You want to get a picture of what your data looks like. You visualize it with a histogram. Okay, now before you have let's say a plot facility, you can do a calculation by hand. Okay, think of the old days where you have to do everything by hand. Well, you can't draw a picture of a histogram, but maybe you can summarize it with something like basic statistics. Where's the mean? Where's the standard deviation? Okay, is it multimodal? Is it kurtotic? Y-tail? Is it skew to the right, to the left? So I put data visualization and statistical description on the same page, so to speak. Now you can think of this as getting insight from looking at the data. This would be something like, well, if you can't paint the picture, you can't draw the histogram, you can kind of summarize it with statistical description. Where is the mean? Where is the standard deviation? What's the maximum? Where's the interquartile? And you did most of that, I think, in year one. Okay, in year one. Now, straight off leading from statistical description, that would be like last class, right? When we draw the histogram. Let me actually draw that up. Hold on. นัดพี่แชร์ทั้งสกรีนใช่ไหมไม่ใช่เฉพาะใช่ไหมจ๊ะ
ใช่ครับ yes
ใช่ครับโอเคครับ so let me draw up the Mathematica. This is from last time, all right? So I think we have an example somewhere where we were playing with I think it was Geyser or Faithful, yeah, something like that, right? Okay, so it's accessing the example data and it's drawing the histogram, let's say. Okay, so this would be the visualization that I was telling you about, right? So for this part, this is a visualization. You're visualizing the histogram. You get the picture. Okay, that's it. That's your insight. Your insight say, well, there's a whole bunch of water spout or eruption that lasts around 4.5 minutes. Okay, and there are smaller eruption that lasts maybe about 2 minutes. So the insight that you might get from this would be something like, well, maybe there are two cavities underneath the O faithful. One is a big cavity with lots of water. One is small cavity with not so much water or something like that. Okay, so that would be getting the direct insight from it. Now again, to go to statistical description, yeah, you would get something like, what's the average number of minutes? Okay, how long does the eruption last on minutes? Now here's a little bit misleading, right? Because the average would probably be something like 4 minutes, 3.5 minutes. But you will never see that because it's averaging the short and the long. Okay, so statistical description, the very basic one would not be enough. Okay, you will have to do something else. Okay, and in statistical description, you can say something like counting the modes or something like that. So there are a way of capturing the information, but still, it's not so much detail, right? So what we did last time was to review probabilistic modeling. Probabilistic modeling, when it comes down to it, just comes down to this. You want mathematical function that traces this histogram. Yeah, you want mathematical function that traces this histogram. Now, how many mathematical functions do you have available? All right, and that's when we go to the this, right? And you say, how many of them? How many functions do you have? Well, in theory, you have about 100 of them to choose from. Yeah, you have 100 of them. Oops, sorry. Show. Okay, you have like 100 of them to choose from, but that gives you the probability distribution over 5 kind of data, right? 5 kind of data. There's a data that's discrete, okay? There's data that is continuous. And for discrete, there are 2 types. One that has like a limited possibility, like a coin toss. One has infinite possibility. So you can go up to infinite, you can go to maybe minus infinity, but it's countable, it's integer, for example. Then you have the continuous, right? Continuous on a bounded interval between 0 and 1. You have a continuous on a semi-bounded, maybe from 0 to infinity. And you have unbounded, completely unbounded, from minus infinity to plus infinity, any value whatsoever, okay? Any kind of any number. Okay, it can be decimal, it can be even transcendental number. Okay, it just covers the whole range. So those are the values that your random values can be. Okay, those are the axis, the x-axis. But the y-axis, when you decide that there are five types, sorry, 1, 2, 3, 4, 5, right? Just ignore the bottom line here. Okay, just ignore this. Just focus on 1, 2, 3, 4, 5 here. Once you decide that it's either finite, like 0, 1, 2, or infinite, like 0, 1, 2, 3 up to infinity, or bounded between 0 and 1, any number, semi-bounded, any number between 0 and plus infinity, or completely unbounded on both sides, plus or minus infinity. Once you decide your random value, what they can be, then you can choose. You still have menu to choose, right? You still have a lot of them. Now, what I did last class was, I think I mentioned, and as you still have this highlight here, the 8 or 9, 1, 2, 3, 4, 5, 6, not this one, forget this one, 7, 8, 9, 10. Okay, so we talk about that. So basically, that's just basically to draw the distribution with function, and that's your mathematical model. Now, my question to you is, if you have the data and you have the histogram, why would you want to draw a mathematical function that fits this? Right? After all, it's not going to be perfect fit. So you have something that's already perfectly fit the data. Why would you want to draw a function to fit the data the best you can, given that you're never going to get the perfect fit? Why would you do that? Well, the reason you would do that is because you believe, and this is the premise of the whole statistical analysis thing, was that the historical data has some noise. So maybe there's a reason why for that period you have a little bit more here than here, but for another period maybe you have a little bit more here than here. So you want something that's more general, more smooth. Okay, something that's not that specific to the data set. So that's why you fit the distribution function. And then you use that to make inference about the future. Okay, now, so that's what we did last week, was trying to review the probability statistics, and we went over quite a few of them. I think under common one. Where's the common one? Where's the common one? Common distribution, right? So we talk about Bernoulli, we talk about coin toss and all kind of stuff. So this all should be reviewed for you guys. Okay. Now, okay. So any questions so far? This is a nice one. I'll show you. This is just binomial distribution, right? Binomial distribution. If you go to Wikipedia, okay, binomial is the number of heads altogether when you toss the coin, head and tail n time. But n can be any number, okay? It can be as big as you like, okay? So, but obviously not infinite. So we go to binomial distribution. So binomial distribution with parameter n and p is the discrete probability distribution of the number of heads, number of success, okay? Success, number of success in a sequence of n independent experiments, meaning you toss the coin n times, okay? Each coin has a probability of landing head equal to p. Now, for most coin, p is 1/2, right? But you can think of this as a sales approaching a client. Each time you approach a client, you have a probability of maybe 1 in 10 of making a sales. Okay, so one experiment, one sales approach has p equal to 0.1. P equal to 0.1. Okay, and then you make independent approach to 1,000 clients. Okay, what is the distribution? What would be the number of positive sales that you can make on that day. Okay, so let me write that down in the notes. Just a quick review. Okay, we work with the common distribution, and I'm just going to highlight binomial. Okay, so you try to sell something, okay, and the probability of success equal to P equal to 0.1, okay, and then you try selling to n equal to 100 person, okay, each day. Okay, assume each person independent. Okay, so if you, the reason it's independent, that means you make a probability of selling 1%, sorry, 10%, 1 in 10. But the next person, you know, doesn't take the cue. It's not like if you make the first person buy, then the second person will say, oh, maybe that's a good thing because the first person bought it, so the probability goes up. No, the probability is the same for everyone. Okay, and it's all independent. So what is called independent, identically distributed. Okay? So the number X of sales you make is X has binomial distribution with NP. N equal to 100 and P is equal to 0.1. Okay? So in Mathematica, that's very easy. We can do this from scratch, right? We can do this from scratch. Okay? You say binomial distribution. Okay? Make it large. Okay? Notice once you type in bi, it suggests all kinds of function that's built in. Now it turns out that this one is the first that comes in, right? It's black because Mathematica recognizes this. It's a built-in function. Now, if you don't know how to do this, once again, go to F1. Okay, binomial NP. So what's our N? 100. What's our P? P is 0.1. Okay. Now I want to look at what? What do I want to look? I want to look at the PDF. F of this thing as a function of X, right? Let's plot that. Let's plot that. Plot this X. Now X obviously cannot be bigger than 100, right? Because you cannot make more sales than you make a 10. It cannot be negative. So obviously it's between 0 and 100. Okay. Now the reason you don't see anything is because when I go to 100, this thing is so thin. So let me draw a small example. Binomial distribution. Am I right? Am I right? Am I right? Okay. Oh, sorry. Bar chart. Oh, okay. I have to do. I think. Okay, let me just copy this. Sorry about that. bar chart. Making life a little bit more difficult, not more complicated than it needs to be. Better one. Oh, discrete plot. That's it. Discrete plot x. Okay, and there. Oops, that's too big. Can't see anything. Okay, how about this? So, okay, and this looks nicer. Okay, what it means is that you're making sales attempt to 10 person. You're trying to sell to 10 people. Each time you have a probability 0.4 of succeeding. Okay, and this is the distribution of the sales you would make on that day. You make no sale with this probability. You make 10 sales with that probability. So, you know, it's almost impossible. You make 9 sales with that probability. Chances are most of the day you would sell 4. So you have like about 1 in 4 probability of making 4 sales on a given day, something like that. Okay. So now you can obviously do this and manipulate. Okay, and instead of making 0.4 here, you make it a parameter p between 0 and say 0.5. Okay. Okay. So right now p is 0. So that's the value you get. Okay. So that's the sort of thing that the probability model does. Now, this is how you build up. This is how you build up probability model. This is a binomial distribution. In real life, the situation would be the opposite, right? The situation would be something like you make the sales to 10 person a day or around 10 person, and then you get histogram of the number of sales you make on a given day. And then you choose this P that fits the data. That's example I was kind of trying to show. Yeah. So this would be some kind of like real histogram, and then you're trying to fit the data. Yeah, that's it. Right. Okay. So that was last week. That was last week. Now, this week, yeah, we're going to review 2 things: linear algebra and calculus. Okay, and hopefully we might get to item set if we can. Now, first of all, let's look at linear algebra. Okay. Raise your hand if you have actually seen the linear algebra video that I sent you. Okay, this was Friday, I think it was. Maybe not this Friday, but previous Friday. Okay, raise your hand. Anyway, so let's look at linear algebra and calculus. Now, first of all, why linear algebra? Why elementary calculus? Linear algebra, okay, let's put this way. Let's make a little note again. We like to make a little note. Okay. Linear algebra. Why? Because you need to manipulate data. Okay? By manipulate, we mean add, subtract, multiply, divide, at least at the minimum, right? Something like that, right? by data, we mean, at least initially, tabular data. Okay, so data that comes in either one index, comes with one index, or two indices. Huh? Now, so for example, think of tabular data. Tabular. X, I, J. Okay. X, I, J. Okay, is some quantity J pertaining to individual I. Okay, so let's start a little Excel sheet. Okay, so this is my I equal to 1, 2, 3, sorry, 1, 2, 3, 4. Okay, this is my I. And this is my J, 1, 2, 3. This is my J. So I, 1 could be Bob. 2 could be, let's start with Alice. 1, Alice. 2, Bob. C, 3, Chris. 4, Dan. Okay, A, B, C, D. Now, J, 1 could be something like height. 2 could be something like weight. Okay, so something like it's 175, 168, 180, whatever, 155. Okay, 4, 5, 7, 6, 7. Okay, doesn't matter, right? So in this case, if I say X 2, 1, I'm talking about the height of Bob. So that's X2, 1. Okay. Now, yeah, the reason this here going from I to J, by the way, it's the opposite of Excel, right? Excel, you reference the column first before the row, but here you reference the row before the column. So just keep that in mind, okay? So why do we want to do this? Because by data, we mean initially tabular data, okay? So if you want to manipulate data, we want to do something like, well, let's make everybody grow by 10%. Okay, let's make everybody grow by 10%. So I can say something like this thing, 1.1, okay? Right? I can do that, right? Now, instead of doing 0.1 times this, 0.1 times this, 0.1 times this, times this, I'm just going to call this thing a vector. I'm going to call this thing a vector. Call this whole thing a vector. And I'm going to multiply everything by 0.1. So in Mathematica, it would be something like, so this would be something like, where's my, okay. Height equal to 170, 155, 180, 140. Okay. Now, instead of multiplying everything by 1.1 here, okay, what I can do is just do this. I have this, I have 1.1 height. right? Now, this doesn't seem like a lot of saving because I can do this as well, right? Yeah, yeah, you get the same thing. Get the same thing. The problem is you can only do for 4 persons. Imagine if you have 1,000. So first thing first, think of the reason you do linear algebra. It's because you're working with tabular data, which you want, for convenience sake, to refer to in lots, right? So you don't have to say multiply 0.1 by the height of Alice, 1.1 times height of Bob. Just say 1.1 times height of everyone. Yeah. So this, again, in Excel you do it one at a time, but in mathematics you do it one time. Yeah, and it does it for you. So think of it that's the first motivation. That sounds a little bit like a silly motivation, right? But in fact, the whole of big data technology is based on modern computer ability to multiply, well, you know, add, etc., a lot of number simultaneously. Simultaneously. Yeah. So you cannot do data analytics without linear algebra. Yeah. So that's why you need linear algebra. Now, when we are going into machine learning, the meaning of manipulate is going to be a lot more complicated, right? It's just not just multiplying and adding, just doing a whole bunch more things. But certainly it just comes down to that. So linear algebra, in short, linear algebra allows you to mathematically manipulate a whole bunch of numbers at once. And then computationally, okay, computationally manipulate a whole bunch of information at once. I'm going to put in quote here because it's not really at once. Okay. So that's why you will need linear algebra. But as with all class, the way I teach most class, hold on, let me. Even though I'm going to work with matrix or vector of size n equal to 10,000 in real life, okay, in this class, probably we work with vector of dimension n equal to 2, maybe 3. Okay. Why? Because we can plot them and so on. Okay, so in this class, so that's the note. Okay, so what do we need to review about the linear algebra? Okay. First thing, I'm going to give you the class note, don't worry. Okay, I'll give you the class note at the end of the class. But I already, I think, mentioned that you have this kind of number, oops, let's make it a little bit bigger. Okay. Okay. And how do you multiply them together? Multiply them. And then you add. So for example, okay. For example, let's say I'm going to I invest my investment is equal to, okay, 0.4%. Oh, sorry, 6.4, that's 40% in stocks and 0.6% in bond. Okay. 40% in stock and 60% in bond. Okay. Or maybe in stock 1 and stock 2. Okay. Now, investment return is equal to, let's say the first stock makes a loss, minus 0.005. Loses it loses 0.5%. Okay, it loses 1%. And the second one makes positive 0.03. So that's 3%, right? Okay. And my capital. So what is my return from investment? Well, that's equal to this guy. Let me write it. Okay, it looks like this. Okay, this is my investment. This is my investment. This is my return. The first one is negative. The second one is positive. Now, is this good news or bad news? Well, it's actually good news because even though you make loss on the first investment, you make gain on the second investment, and you make more investment in the one that you in. So it's minus 1% on 40%, but you add 3% on the 60% that you get. So what's your return investment? That should be minus 0.01 times 0.4 plus 0.03 times 0.6. Okay. So you get 1.4%. Now, when you do this with just two numbers, you can just write it. Okay. But now imagine that you are professional investment. You are actually investing in 50 different stocks. Okay. So how would you do it? You would say my investment dot investment. Oh, sorry. Investment return dot. Now notice it's all blue because I haven't typed in. But once I type in, this dot this is equal to this. So it's the same thing as that. Okay. So my question is, well, what else is matrix linear algebra good for? Okay. Enjoy. So that's one thing. What other reason? Well, it turns out that you can use linear algebra, especially matrix multiplication, to represent system of equation, system of linear equation, right? So instead of saying, okay, I want AX ax plus by equal to, let's put in real number, okay? 3x. I want to write 3x plus 7y, okay, is equal to 17, say. And I want to say, yeah, this is a text. I want this one, and I want something like 5x minus y is equal to 3, something like that. Okay. Now, first of all, I want to write this in a matrix notation. I'm going to take the matrix of coefficient. So what's my matrix? It's going to be 3 and 7, 5 minus 1. Yeah, that's my matrix A. My A matrix. Okay. My variable equal to x and y. Okay. And then I'm gonna say that right hand side equal to 17 and 3. Okay. So the equation I'm going to write is actually A dot variable, okay, equal to, okay, let me see. Yeah. So this is what I want to write.
Professor ครับ can you move up a little bit ครับ I can't really finish typing.
Okay,ครับ. Basically a matrix, right? What do I want? I want 3, 7 on the first row, and the second row I want 5 and minus 1, right? So I'm just gonna write a matrix, okay, and variable. So you see that?
Professor, how for mine is said that the track class is protected เหมือนแบบมันพิมพ์บวกไม่ได้
Which one? Oh, okay.
3x บวก 7y
No. 3x บวก 7y. Oh, okay. Try this. If you write something like this, does that work?
I'll try.
Okay. Does that work? Does that work? Okay. Now, obviously, you can't do this because this is an assignment. I'm not making an assignment. Okay. This is not valid. So that's why I write in this pure text. Okay. But this is what you want to write. Okay. I want to solve, basically, I want to solve this. This is what I want to do. I want to solve this. Yeah, that's what I want to solve. So it's not an assignment. I want to solve this for x and y. That's basically I want to do. Right? Yeah. So this is how you would write equation. Now in English, this is what you want to say, right? You want to say solve x and y such that 3x plus 7y equal to 17. 5x minus y is equal to 3. This is in English. Okay. Okay. Now in Wolfram, you have to write. You can't use the equality sign. I think when you had the problem was because you used the equality sign. It's considered an assignment, right? So you have to do this. It's equality twice. Yeah. You guys remember that? In Mathematica, is an assignment, whereas is a relation. Okay? Does that help? Sorry, who was that? Does that solve the problem, Kap? Hello, Kap?
I think it's okay now ค่ะ เดี๋ยวค่อยไปโน้ตตรงอื่นก็ได้
Okay, Kap. Okay. So basically, this is what I want to do, right? In mathematics. In mathematics, right? Mathematics. Okay. Now, in Mathematica, I can write this. Let's write this exactly. I want to ask Mathematica to solve two equations. So that's my system of linear equation, right? 3x plus 7y equal to 17. 5x minus y equal to 3. I want to solve it for x and y. And that's say, oh, x is equal to 1, y is equal to 2. That's my answer. That's my answer, right? That's my answer. Okay, so let's try something else. Let's try something else. Let's try same thing, but now I'm going to change the right hand side. I'm going to make this 18. Okay, see what happened? Well, now I get different answer. Okay, right? So anyway, so this is what Mathematica does for you. It solves analytically the solution for you. But this is rather clumsy, right? This, if you have 500 equations, you have to write this 500 times. Okay. In reality, you can represent all this one time. So I'm going to say solve. Okay, I'm going to call this. Let's see if this works. Solve a matrix dot variable equal to right hand side and solve it for variable. See? Okay. So yes, Mathematica will solve this for you. But if you do this and you have 500 equations, you have to write this, you know, in details. Now you can imagine if you have 500 equations and you have, you know, 2000 coefficient, but instead of doing this, you have like a spreadsheet or an Excel, okay? Spreadsheet. In fact, we can do that. We can say that this is 5. What's the question? 375 minus 1. 375 minus 1. Okay. And let's save this as CSV. And this is my A matrix. Okay. Let's go to my class. Okay. Okay, that's my A matrix. Here, okay. Now watch this. Okay, first I write everything. Now, if I didn't write everything, I can reference to it by this. Now, in reality, imagine you don't have just 2 by 2. but you have hundreds by hundreds. Okay. So I'm going to say set directory to the notebook directory. Okay.
อาจารย์ครับ
ครับ
What does this do, like set directory?
Oh. What this does is, oh, okay, I haven't said this. Okay. It means that I don't have to go to other folder. That's all. This is basically where am I? Where am I? I'm right here. I'm right here. Okay. So in your class, because I teach a few class and I have a few projects, I put everything that has to do with your class in one folder. So now I put all this sample here. So I say I set this to the directory. Okay. Whatever it is. Okay. It doesn't matter. In your case, it will be a different number. Now the point is, I want to say my A matrix is equal to import, right? Notice import source format. Okay. Yeah, my matrix is import. What's the name of that? A matrix. A matrix. Let's go. This time. Yeah. But because I already did the notebook directory, I don't have all this to. Okay. So that's my matrix. Oh. Sorry. I meant to do this. Okay, let's erase everyone. Okay. Now notice I'm gonna do this, right? I'm gonna say this is my A, and I might as well put B on the right hand side. Where's my B? Where's my B? B is 17 and 3. Okay. 17 and 3. Okay. Okay. So let's try that again. Sorry, my bad. Yeah. So see, this is the same thing as this matrix. Right? 3, 7, 17. 3, 7, 17. 5 minus 1, 3. 5 minus 1, 3. Okay. So I want 3 and 7 and 5 and 1 to be my matrix. Okay. So this is my data. Okay. Matrix M, my matrix is equal to data. I want what? I want all the row. Okay. And only 1 to 2. Okay. My matrix. My right hand side is equal to data all comma 3. Now see if you follow this. Okay. My CSV file looks like this. My CSV file looks like this. So when I read it in, I get this. Right? So the first row is 3, 7, 17. Second row is 5 minus 1 and 3. Now, I want this to be my matrix. So my matrix is all the row, the first 2 columns. All the row, the first 2 columns. My right-hand side is all the row, but only the 3rd column. All the row, but only the 3rd column. So I get this. Okay. Now, I ask Mathematica to solve for me. Solve, okay, my matrix dot, say, variable equal to my right-hand side. Solve for yeah, see, and that's your solution. Now, obviously, obviously, I'm doing a lot of work to just solve 2 equations in 2 unknown. Yeah. But you can imagine that instead of having just this, you can have, 5,000 row and 5,000 columns. Yeah. So this demonstrates that likewise, just as you want to manipulate a whole bunch of number at once, now you can say you can solve system of linear equation with many variables. Okay. What are the reasons? So that's it. Okay. So why do you want linear algebra? Okay. So here, and or solve a whole bunch of equations simultaneously. Okay? Now, computationally, it's the same thing, right? Computation, solve analytically, numerically. Okay? Right, I would put 1 and 2. It's the same thing. Okay, mathematically or okay. In real life, of course. In this class, yeah. So it looks like I'm making a lot of big fuss just to multiply 2 numbers together, right? I'm just multiplying 2, 3, 4 numbers together. The point is you can do this with a very big matrix. Now, this is using matrix algebra to represent system of equation. Okay, so that's what you want to do. You want to represent system equation. Now, what else can you do? Mathematician worked out matrix theory. Okay, theory about linear algebra. Okay, and that allows you to analyze system of equation and also tabular data. Okay, so that's a logic here. Okay, let me go back again. Why linear algebra? Because you need to manipulate data, right? Manipulate is basically all this operation. In big data, you want to do it for the whole bunch of numbers at once. So you want to do it on a big vector, a big matrix. You don't want to do it to just a few numbers. In this class, you would see just a few numbers, obviously, because It's a class, right? But aside from keeping a whole bunch of tabular data in vectors and matrix, you can actually use the data format to store coefficient of your equations. Yeah, so you can use that to solve system of linear equation. Well, that's not all that interesting if that's all the mathematicians have been doing. But the mathematicians have worked out what's called matrix theory. And this is a big class. Okay, you don't have the whole class there. But that allows you to analyze system of equation. Okay, also tabular data. And I'm just going to give you one example. One example. Okay, and that example is 2 equations in 2 unknown. Okay, 2 equations in 2 unknowns. Now, we just did that. We just did that. Yeah, so that's not all that interesting, right? That's not all that interesting. Okay, now what if I change a little bit? I want to make my A matrix into something like yeah, I do this. Yeah, I just came up with a different number. Now I try to do the same thing. Look what happened. Oops. My new matrix. Okay. What does it say? Okay. Notice when my matrix is this. So when my matrix is this, okay, the matrix is this, I can solve it. When my matrix is this, I don't get any solution. Anybody wants to tell me why? Okay. Well, let me try something else. Okay. Let me make my new right-hand side is equal to, okay, my new right-hand side is equal to 10 minus 20. And I want to solve this now. My new right-hand side. Okay. Anybody saw that? Okay, there are 3 situations. Let me just erase this to show you. Okay. I'm just gonna. I'm getting 3 responses here. Okay. First response, I get a solution. Big solution. X is equal to 1, y is equal to 2. Second, I get no solution. No solution. No solution. Third, I don't get a solution, big solution. I get combination. In fact, I can put in any number here. I can put in x is equal to 500. Okay. And y, supposing particular x is equal to this, particular y is equal to this, and I put in this. Okay. It turns out that this one is a solution. Okay. This one. You want to check? How about this? My new matrix dot particular x comma particular y equal to my new right hand side. True. Okay. Now, some of you are looking confused. Okay. Okay. Some of you probably know exactly the reason. Okay. You haven't spoken out, but you know exactly the reason. You have two systems of linear. You have two linear equations. You have two linear equations in two unknown, x and y. In one situation, you get a precise answer what x and y is. In one situation, you don't get any answer. In another situation, you get any combination. So if I put in another number, say another one, 5,000. Okay. Yeah. This is still true. It's true for any number. Okay. It's true. It's always true. Okay. It's not just 1 and 2. It's any combination would work. Okay. Now, anybody wants to tell me what's the insight for all this? Well, two situations. You have 3 situations. Situation 1, you get unique solution for the 2. Situation 2, you don't get any solution. Okay. And 3, you get plenty of choice for solution. Okay. Now, how do you sort this out? Well, the easiest way to do this is to look at it this way. I'm going to plot. Now, I meant to get you a tablet. Okay? When I have this equation, okay, ax plus yb is equal to c. Okay, that's the same thing as, okay, it's supposed to be, sorry, free text. Okay, if I write this, it's the same thing as y is equal to minus a divided by bx plus c, right? Right? Anybody see that? Okay, I just put this over here. Okay, and then I take b and divide by this. Right? What is that equation for? That's the equation for line with slope minus a divided by b and intercept c divided by b. Correct? Right? Right? So when I write this, what am I saying? Yeah. So when I write this, okay, what am I saying? I'm saying y is equal to, now I take this over the right hand side, 3x plus 7 and divide by 7. Correct? Right? And what am I saying here? Well, in this case, I'm just going to move y over here. Okay. Can anybody not see this? Okay.
Can you scroll up a little bit?
Yep. I have these two equations, right? But instead of writing 3x plus 7y equal to 17, I put x on the other side and I divide everything by 7. Here, I put y on the other side and I don't have to divide it. So basically, it's the high school equation, y is equal to mx plus b. You remember that? Y is equal to intercept. So y is equal to slope times x plus intercept. Yeah, you remember that? Okay. Now, so when I did that, I get two equations. Okay. So obviously, mathematically, it's going to look like this, right? This is y is equal to, okay, it's just some arbitrary, okay? You can work out the precise number for the example I used. But this is y, this is one line. Okay, this is one line. And the other line is this. Okay. Now, if you make one line this way and the other line this way, it obviously has to intersect at a point, right? Correct? That's what we mean by getting a solution. Okay. Now, notice, okay, notice. How can we make it not have a solution? Yeah, just to make life simple, I'll show you. Two lines that are parallel. Oops, it's a bad line. Never meet. Okay, so this is situation number 2. You conclude that because two lines intersect. Okay, because two lines are parallel. Now, what's the third choice? What's the third choice? The third choice, you get plenty of choice because, well, what's the solution that you get? You get this, right? So that's the same thing as saying y is equal to minus 3 over 7x plus 10 over 7. In other words, the reason you get combination is because you put in two equations and you get back one equation. So in other words, two lines are the same. Let me say that again. Yeah. Okay. So you have three situations in life. And this, I'm going to generalize this. I'm going to generalize the heck out of this because this is, by the way, this is how you analyze a problem. You will definitely have three problems in life. Okay. Whenever you see a problem, you come into three situations. You get a unique solution because the two unknowns intersect. So that's the first situation. Second situation, you don't get any solution because it's parallel. Third situation, you get as many solutions as you like because the third line is exactly the same line. It's one on top of the other. Now, how would you spot that? How would you spot that? Well, it's obvious, isn't it? Watch this. Let me write the number here just so you can see. Let me try again, okay? Now, you wanna type this in. Yeah, I'll give you time to type this in. Now, this here, 3 and 7. If I move the y to this side, okay, it's gonna be minus 3 over 7, right? If I move y over here, it's 5. So it has different slope. Okay? Two lines, different slope. Okay? Two lines, different slope. Now, So you get that. Now let me cheat again. Let me do it again. I'm going to write the other one. The other one is, I think, minus 6. Okay. Minus 14. You don't get any solution. Why? Because if I move y to the other side, you get 3 minus 3 over 7. If you move over here, 6 minus 6 over 14 is the same thing as minus 3 over 7. In other words, I just multiply minus 2 here, minus 2 here, and I get this. So the coefficients are related. They are, okay, this is 3, 7. This is minus 6 and 14. So the slope is the same, but the right-hand side don't play along. What if I do this? The left-hand side is 3, 7 becomes minus 6 minus 14. And the right-hand side, I make the same rule. Multiply by 2 and subtract. See? Right? So maybe if I put this here, it would be more obvious. I put it here. Okay. Can you see that now? Okay. The left-hand side, the ratio between the coefficient of x and y are different. Okay, so they have different slope. Here is 3 to 7. This is also 3 to 7. So same slope, 2 lines, same slope. But the right-hand side don't play along. Here, 3 to 7 to 17. Multiply point minus 2, you get this. So basically, this is equation multiplied by 2 and put a subtraction. So it's actually same equation. So you actually same equation. And same equation. That's it. Same equation. Same equation. Okay. So because you have 2 equations, but you actually have just 1 equation and 2 unknown, all you get is just that line. Okay. So in fact, you get this line. Now, how do I make this mathematical? To say that this thing is the same ratio as that is to say 3 to 7, 3. I want to say 3 to 7, same ratio as minus 6 to minus 14. Okay, how do I say that? Well, I do this. Right? Okay. Or alternatively, I can say 3 times minus 14, 3 times minus 14 equal to, right, 7, okay, times minus 6. Or 3, I'm going to take this out, times minus 14 equal to 7 and minus 6. Okay, so I take this out, minus. Okay, you guys agree that these are the same equation? So the situation like this, you don't have to worry about. 2 lines, 2 different slope. You want to play same slope, but same slope can be inconsistent or consistent. But you want to check that they have the same slope. To check that they have the same slope, the ratio between the coefficient has to be the same. So 3 to 7 is the same as minus 6 to minus 14. or 3 times minus 14 is equal to 7 times 0.6 minus 6, or 3 times minus 14 minus 7 times 6 is equal to 0. Now, I'm going to do this in a more general form. Instead, I'm going to say A, X, B, Y, C, X, B, Y is equal to right-hand side 1, right-hand side 2. Okay, I'm going to solve this. Now, the reason, what I want to check then is A times B minus B times C is equal to 0. Okay, so okay. Notice the reason I put this check equal to 0 is because it appears on the bottom. That's the reason why you don't have any solution. Because this thing here, this comparing the ratio, i.e. coefficient, i.e. comparing the slope, is equivalent to checking whether this thing is equal to 0. So, in other words, this quantity determines whether the system of equation can be solved for unique solution. Okay? In the general form, this is what it's called. This thing is called, hence it is called determinant of the matrix 3, 7, minus 6, minus 6, minus 14. Okay? Now, I'm saying a whole bunch of things here. Okay? I'm saying a whole bunch of things here. But it's rather obvious, isn't it? You only have 3 situations. You have, again, this situation. You have this situation, or you have this situation. Okay? So, what separates the first situation from the second 2 situation is whether or not the slope is the same. If the slope is the same, then this ratio is the same. If this ratio is the same, you take this to the left-hand side, it's equal to 0. That thing, I call it determinant because it is this quantity. If it's 0, you have to divide something by 0. And this is no. If BC is equal to 0. Okay? That's why it's called determinant. Now, working in general form, my matrix is equal to A, B, C, D. Okay? determinant of my matrix, okay, is this. So when you go to DET and I want you to press F1, this gives the determinant of the square matrix. That's everything we've been doing. Now, the reason it looks trivial is because this, right? A, B, C, D. But the point is, what if you have 1,000 by 1,000 matrix? Okay. You have 1,000 equations in 10,000 equations in 10,000 unknown. Okay, mathematics says don't do anything, compute determinants first. So this is an example. If you want an example of how mathematics matrix theory allows you to analyze huge system of equations. Okay. Now, because in our class, let's look at tiny system, two linear equation. So that's it. Okay. So situation one, you get unique solution for two unknown because two lines intersect, i.e. determinant of the coefficient matrix is not 0. Otherwise, you have the following two situations. Okay. Now, what kind of data analysis are we doing here? Well, this is, in a way, you're solving system of equation. In your data analysis, you'll be solving system of equation as well, but the situation will be more involved. So I'm not going to, be able to say how many times you're going to run into this kind of situation because you run into it all the time. Okay, so you always have to solve system of equation. Okay. So you can think of it this way. You can think of it as something like, let's say you are planning, say, healthcare vaccine program. Okay, and you have some kind of demand equal to supply equation. You have some kind of production equal to factory capacity. You have something like a cost of vaccine is equal to amount you have allocate in the budget. Something like this. Okay, so this would obviously be something like 3 equations, and maybe you have 3 unknown. But instead of having this, you have 1,000 equations in 1,000 unknown. This is your data. Data analytics in this case means you analyze whether or not this problem is solvable. Okay. Now, let me be honest with you, and this is from real life. Okay. In this situation, in class anyway, in class, you will always be given this situation. Why? Because you have to have the answer, right? So this is how you solve in high school. When you were a kid, you were saying something like n equation in n unknown gives you the solution. What it means is that n equation that represent this system of equation has a solution. Okay, so that's it. That's what you've been doing. So from this situation here, this is the situation you encounter in grade school. Okay, now what happened here? I'm gonna say this is the situation you encounter in real life, and you need to go to engineer to change something so that you get a solution. This is a situation you get in life. Okay, so this is my confession. This is what you get in real life. In this situation, you get this in high school, in grade school. In real life, you get this. Go to engineer. Get a solution. Now, this is the situation you encounter in real life the most. Okay, so, and your job is to choose amongst the possible solution which one is best. Hence, optimization. Okay. So again, it looks a little bit dry because I have to type, but you get the note. Okay. Situation one. This is what you get in grade school. Situation in real life, sometimes you get this. And you have to go to engineer, or you have to go to a meeting room. So there's some kind of conflict that this line and this line never get along. So somehow you have to get to a compromise. So you either go to the engineer or business planner or client or factory. Okay, somebody has to bend. Somebody has to bend. And when somebody bend, that means you get a solution. But most of the time, you get more than one solution. Your job in life is to say, this one is best. Okay, why would you do that? Well, maybe you have some kind of criteria. So this solution would be something like a road you can take. But there's only one of them that is closest to something you like. So this would be a profit. Okay, maximization. Okay. And this is why your job is to choose amongst the possible solution which one is the best with respect to some criteria. Profit, hence. So this here means that So linear algebra, number one, okay, you can manipulate whole bunch of numbers at once. Two, you solve whole bunch of equation simultaneously. Three, with matrix theory, you can analyze huge set of equation before you even try to solve it. Now, this means this is your job as data analytics. You analyze the problem, you analyze your data set, you get the solution. But data analytics techniques, statistical methods, and machine learning also are based on this. Okay, so that's it. That's why you need. That's why you need what's the date today? 7. Okay, that's why you need this. So that's it. That's matrix algebra. Why you need, okay? Okay, so